मधुराधिपतेरखिलं मधुरं वचनं मधुरं चरितं मधुरं वसनं मधुरं वनितं मधुरं चलितं मधुरं भ्रमितं मधुरं मधुराधिपतेरखिलं मधुरं वेणुर्मधुरो रेणुर्मधुरः पाणिर्मधुरः पादं मधुरं नृत्यं मधुरं सख्यं मधुरं मधुराधिपतेरखिलं मधुरम्.
In the world of technology, the smaller the chip, the bigger the leap. This world we live in today wouldn't be conceivable if it were not for the crucial parts that electronics played in it. And as engineering students, we do and should know the importance of this industry over the globe today. A great day to everyone joining us today. With the global powers fighting fiercely for a piece of the semiconductor manufacturing and design industry, India has also started competing. Recently, the country has attracted investments from global companies like IBM and STM Microelectronics to establish chip manufacturing facilities. Several acquisitions, partnerships, and research and development initiatives are contributing to the growth of the semiconductor industry in regions like Bangalore, Noida, Gurugram, and Uttar Pradesh. And now that the world knows our journey is afoot, let's offer a grand welcome to a nationally famous semiconductor analyst, Mr. Arun Mampazhy, sir. He is an IIT Madras graduate in electrical engineering and has completed his master's in the University of Maryland, USA. He has specialized in semiconductor devices, microelectronics, and integrated circuit fabrication. He currently works part-time at IIT Roorkee on another passion of his Indic knowledge systems and Sanskrit. After more than a decade of industrial experience, which include being a member of technical staff at IBM India and manager for multiple teams at Global Foundries India, Sir has taken initiatives to share his views, statistics and information and the globe trends and needs of the industry and actively works towards shaping a country on his multi-decade-old dream. Wanting to see semiconductor fabs, especially silicon-based high-volume fabs in India. Welcome you to Amrita, sir, and we are keen to learn from you today. Please join me in giving a warm round of applause as we welcome Mr. Arun Mampazhy, sir, onto the stage.
Thank you. Namaste, Vanakkam. Thank you for the introduction. Thank you, Dr. Amit, for taking the initiative to invite me here. Thank you to the head of the department and other faculty members. Hopefully, in the next hour or so, let's explore the world of semiconductors and chips, not potato chips, not banana chips. I come from the world of banana chips, Palakkad, but this is semiconductor chips, electronic chips. All right, how is the crowd here? How many of you are triple E? Wow, almost all. Anybody who's not triple E? None. Oh, all right. Within triple E, first years, second years, first years? No, second years? All right, third? Okay, fourth? Okay. And that's so mostly BTech or masters, PhD, masters, PhDs. Okay. Okay, great. Within BTech or masters or PhD, anybody with a bit of microelectronics or VLSI specialization? You are, okay. So rest of you are. How does it work for BTech? Do you have to choose something in the final year or so in terms of the project, microelectronics project, embedded systems, circuits, microelectronics, nothing? Or clueless? Okay, with the final year project, anything to do with VLSI at all, whether it design or not sure about that. Okay, never mind. Let's see. Okay, so the title says India Semiconductor Fabulous Future. So it gives away straight that I am a person who strongly believes that India needs to have chip fabrication units, high volume chip fabrication units, specifically if possible silicon fabrication units. What that is, what it means, we'll see later. So you know, the word or the part which was not mentioned in my introduction is I'm a fab fanatic. Okay, with that said, this is how the talk is structured. Give an introduction to electronic semiconductor chips and a lot of information on the industry and a little bit on the surrounding ecosystem. Then we'll have what India is trying to do. So I'm sorry, I didn't catch your name, the person who gave the introduction. Sorry? Dikshita. So Dikshita mentioned a lot about you know, so many places, so many companies. Really? Are they really happening? We'll see. Okay. Then some of the feeder industries in software. So a lot of people have this notion that there is a narrow field of semiconductors and so on, but the fact of the matter is almost any department in this university you take, there's going to be some connection to the semiconductor world and fabs. So we'll see that. And what are possibly the opportunities as individuals, as a university, as researchers, and so on. So we'll start with the base of the pyramid. Let's start with Wikipedia, right? Or as we Malayalis might call it, Wikipedia. All right. So this is in a nutshell the different variations you can find in electronics. You have B2B e-commerce, mobile technology is one big chunk of it, e-commerce, consumer electronics. So what is the different? Anybody can name what is consumer electronics here? Give a couple of quick examples. Phones are already in the mobile. Right, you guys are still all students, so nobody can think of washing machines and right, those are all your mom and dad stuff, correct? Right, so that's the consumer electronics, and then you have semiconductor industry. So you know, there is a bigger chunk of electronics, and then semiconductors is mentioned as one part of it. So then why is it so important? So that hopefully you'll get an idea by looking at this. Does this have a pointer? I hope. Okay. So it says the semiconductor content within the electronics, and this is the year 1999, 2000, and so on, and it goes on until 2021. You can see that the amount of semiconductors within an electronics product on an average has been steadily going up. Now it's almost 1/3 on an average semiconductor. So this is where semiconductors become important. Hopefully you're all used to your teachers asking you questions in between, so please don't mind me asking. So let me quickly ask you, is resistors a semiconductor? No. Capacitor? Then what is semiconductor? What is a semiconductor? Diodes are semiconductors. Excellent. Transistors are semiconductors. Okay. All right. Good. I'm glad, you know, we have a common language. So this is the picture of a what? What is it a picture of? Well, there are ICs in it. What is the bigger one? Motherboard. Great. So whatever you see in here as these, what are they called? Sorry? ICs. What is the full form of ICs? Alright. So that is predominantly semiconductors, except for the casing, maybe everything else inside it is semiconductors. Then you might find some, what are these little things? Capacitors, inductors, right? Transistors. So why transistors outside the IC? Alright, Never mind. There might be some special purpose transistors or power transistors and things like that outside. Resistors, capacitors, passives, inductors. Inductors in particular sometimes are rather huge, so they might be outside. I'm not even a systems guy, so I don't even know what might be outside. I focus mostly on the IC side. So what does it say? Can you read any company name in any of this? Does anybody find any company name anywhere? Huh? Okay, and what is this? ST? What is ST? Okay, that's ST Microelectronics. So most likely ARM is the IP owner of that chip, or the, you want to call it the designer of the chip, and the chip might be actually, well, ARM is most likely the IP owner. ST Microelectronics probably the final designer and the fabricator of that chip. Okay, what all this means will come in a minute. So this is how big is this industry, the semiconductor industry. I'm not talking about the electronics industry, the bigger chunk, but just the semiconductor industry right now hovers around somewhere around $600 billion of annual revenue. So all the companies that are involved, all the companies which can be called as semiconductor companies, annually on an average make about $600 billion. A small caveat at this point, some of my slides might be a little old, but then I've still chosen those because the kind of format that those charts are, unfortunately the latest ones are not available. So some might be a little old, but never mind, the trend is almost the same. You will see the growth of these going up and down a little bit. It's a little, the semiconductor industry is a little cyclical in nature, goes up, down, but the downtrend is a small down, and when it goes up huge. So overall, if you take, if you draw a line like this, it keeps going up on an average. All right, and this $600 billion is expected to reach about $1 trillion by the end of this decade, and then by 2035 or something it might become $2 trillion. So it took 50 years. Anybody wants to guess when was roughly around what time was the first IC, first integrated circuit? '70s. Great, thank you. So 70s, right? So it took about 50 years to get here, but now it is going to be quantum jumps from here, because it's going to be exponential from here. Okay, so now what are all these, right? So this is a mobile phone. I don't think anybody has this kind of a phone now, but this is inside of some mobile phone. I got it from the net. You will see multiple ICs, right? And what are their purposes? So some of them, if in case any of you are there in RF systems and so on, might understand. So you'll have antennas, network IC, audio IC, flash IC, charging IC, power IC, CPU. All right, the cute little guy sitting here, and then memory wise RAM. So many such semiconductor chips inside one mobile, right? And what is inside each of these packaging? You fabricate them on a paper-like wafer, right? You will have multiple of those chips, or what I call here as die. Each little die here eventually goes and gets packaged like this and goes inside your phone. Okay. Any guesses on what is the size of that wafer? I'm already showing it to you like this. So anybody wants to guess what is the size of that wafer? It's a silicon wafer. It's a, start with a plain simple monocrystalline silicon wafer mostly. There are some other materials used. I'll come to that later, but big silicon wafer is a starting point. What is the size of it? Take a chance. I can't even see your faces. All right. So this is the history. Oops, sorry. Let's go back on that. In the 70s, the diameter of this thing was about 100 millimeter. 80s, about 150 millimeter. 90s, 200 millimeter, and 2001's 300 millimeter. There were attempts to go to 450 millimeter, but it became too big to handle, and there were issues of possibly breaking and so on and so forth. Anybody wants to quickly convert them into inches? How much is this? 150 mm is what inch? 6-inch, great. This? Math, not semiconductors, just math. 8-inch and this is 12-inch. Okay, so you might, I just mentioned that because you might keep hearing this 8-inch and 12-inch and all. So these are the size of the starting wafers, and you might think it's simple, but it's not as simple transitioning from one size to the other. Your equipment, the tools that you use in the fab more or less completely changes. Okay, now keep this in mind. I'll have another quiz question 2 or 3 slides later. Keep these years and keep these sizes in mind. Okay, and this is just shows which company has how much capacity of which size and also if you read some of these material literature, if you read my articles also, I'll keep mentioning about 300 mm fab and 200 mm fab and so on and so forth. Remember, that's the size of the full wafer that you start with. It's not the size of the transistor or anything like that. Those are in nanometers, as you would already know. Again, this just shows the capacity of some of these companies. So Samsung, a bit old chart, you will see 300 millimeter wafers in up to 150. They are all still in use, but 150 200 mm fabs are old. The new ones are mostly only 300 mm. Okay, now coming to a little bit of device, semiconductor device physics and so on. If hopefully you might learn in your second year or third year or masters or PhD. So PPA, right? Performance, power and area. Take your mobile. What does performance mean? Space, the amount of memory in it. Okay, fine. Bit falls under the area side, but anyways, what else? Speed, great. Okay, do you want the speed to be higher or slower? So you want the performance to be higher. Power, lower. My mobile is already running out of charge, right? You don't want that. Area, small, except for fashion. I don't know if you've seen some of those laptop sized tabs and people used to, now I don't know if it's there or not, they used to keep it there on and talk like in a phone. So except for that, you want these things to keep shrinking, right? Or put it in another way, I did bring a pen drive also as a backup. I don't know, you guys, if I tell you this story, I'll be giving out my age, but these things used to, this size pen drive in, I don't know, early 2000s probably could hold what? 256 MB, 512 MB or something. Now what is the this is not the latest one. This holds like a few GB. But what is the latest that this can hold? 1 TB, 2 TB. All right, something like that, right? So the area is shrinking, or in other words, within the same area, the amount of memory and so on is increasing, and same with the processors also, whether it's CPU or GPU. Within the same area, you're packing more and more transistors. So how is that possible? I'll just go back into this, and so remember this one little die here. Inside or in that die, you have this entire, from the transistor level all the way to the connection level fabricated, right? So how does that one look like? If you take a cross section, it will look something like that. Your little transistor is somewhere down here, and then you need to build all the way the connections, because imagine you have millions or billions of transistors at the bottom level, right? And how many pins do you see on an IC at the top? 20, 30, right? So these millions or billions of transistors are eventually connected to this 20 or 30 pins on the IC on the top. So naturally it involves a lot of layers of wiring and so on, plus some additional special transistors, special devices. There are resistors, inductors and capacitors built in within this die itself, and so that's why it's called an integrated circuit. All of this is integrated into one. If you look up your textbook definition of it, an IC, it probably says all of these things integrated into a single monolithic silicon wafer, right? That monolithic means, in just one piece of thing you have all of this built. So now how does this power, performance and area come into picture? Just the least amount of device physics. I don't intend to go too deep. So you have your channel length, How many of you know this stuff in terms of gate, MOSFET, right? Gate and the source and the drain and the channel, and how does the channel switch on? Just raise your hand if you know some basics. All right. Okay, not bad, right? So tell me, if you keep shrinking the channel length, how does it become faster or slower? Shrinking the channel length. Slower, faster, right? Because electrons need a smaller length to travel. Okay, your travel length is smaller. What about the overall size of the device? Right, so area shrinks. It's not just the channel length, one dimension shrinks, everything else shrinks accordingly. Okay, and finally the power. So that is a function of the turn on voltage, the gate voltage that you apply. You need a smaller voltage to turn on the channel. So this is a basic fundamental principle of why people are so crazy about, I think in the introduction she said smaller the chip, what did you say, better, right? But again, doesn't apply for potato chips and all of that, just for semiconductor chips. Okay, now we get into the real industry. So all of this so far is academic, right? Textbook stuff. So now it gets into the industry. How are these things made, right? So many chips, so many kind of chips. Is it just one factory doing it? Is it just one company doing all of it? No, it involves an entire ecosystem. Little bit of research, but industrial research is way different from an academic research. I'll come to that later. The design side, how many of you have any connection at all to some kind of design? Use what are those tools? I forget, Spice or something, or any of those tools, and do a little bit of VLSI design. Anyone at all? Okay, the master student does. None of the BTech students do. Okay, maybe somebody from the faculty can help me. Is there a VLSI department at all with the BTech course? Not sure. Oh, it comes under ECE department. All right, get it. Okay, then you have the manufacturing side. So again, for design, you have these things called intellectual property. And by the way, just since that came up, right, AAA doesn't matter, AAA versus ECE in this particular case, because hardly these courses are hardly there in India anyway right now, right? So this whole thing is now being built, and we are behind. We are lost already 30-40 years, but we'll catch up on that. I'll be talking about that at the end of it. So this stuff is going to be useful for any of you. Electrical, electronics, doesn't matter. Okay, design side, you have IPs, which are basically, imagine you have these millions or billions of transistors. Nobody is going to sit and design each and every one of these transistors and how they're connected and so on. You have something called standard libraries. You just make an entire block, and that block functions as a register, or that block functions as a accelerator or whatever. And then these designs are patented, or they are licensed for a fee. So the companies can just buy it, use it, the whole block. But then the company needs to know how to combine these blocks. How does each of these blocks talk to each other and so on. That's the job of many of the design engineers. You buy these IPs. So that's the IP side. And then you have electronic design automation. So these things are not done on a piece of paper, or not even on a standard computer. You need EDA tools, electronic design automation tools. There are kind of big three companies, Synopsys, Cadence, and one more, which I don't know, which one did I miss? Never mind. So they provide these tools. They're very costly, and design companies have to buy it. This is part of the reason why universities do get some of these at a lower rate, but again, it's not the full sophisticated package of EDA. But students can play around with it and so on, and it's in the interest of some of these companies also to promote this in universities, because once the students get used to it and they graduate, they can easily, so the companies can save money on their training, right? So that's the picture here. And then on the manufacturing side, this is where the fab comes into picture. This is where the chips gets fabricated, right? And then packaging and testing. And in the manufacturing also, you supply raw materials, including the starting silicon wafer. Then the equipments, they are the costliest part of a fab. Some of those equipments can cost like $100 million a piece. Just one equipment will cost $100 million and so on. And you need hundreds of them. So add up the cost. All right, this just to show how globally each country does in some of these. This is kind of the design side. If you see the value addition, they add up to probably around 50%. The fabrication side about 20-25%, and then out of that the packaging side is only about 6%. Countries, US in blue, very strong in EDA and core IP. Again, within that it's divided into logic and analog and memory. If anybody is interested, I can take that question at the end. What is the difference between logic, analog and memory? Equipment makers, you might have heard names like ASML, Applied Materials. Again, US is quite strong. Wafer fabrication, US is kind of come down because Taiwan picked up a lot and China also picked up a lot. So if you ever heard recently about this US-China war conflict going on in terms of semiconductor chips and equipment and so on, it's because US realized that its manufacturing share, its wafer fabrication share has gone down, and China has picked up a lot, and US wants to regain its strength in wafer fabrication. I'm giving a talk tomorrow, in fact a panel discussion tomorrow in Chennai related to that topic, so I do have the slides for that also ready, but just in case there's a question I can show those slides. I'll quickly go through it because it's a little more deeper. There are two models here. One is and what is called as a fabless and foundry model, and another is called an IDM model. Essentially what it means is that because the fabrication of the chip started becoming quite costly affair, at some point the guy who's the inventor of TSMC, Taiwan Semiconductor Manufacturing Company, he got this brilliant idea that why not we separate the design side of things and the fabrication side of things. So there were companies starting with TSMC which started focusing exclusively on fabricating the chips, and then that helped some of these design companies separate them out. They don't have to worry about the capital needed to establish a fab, so they started focusing only on the design. So that's the fabless, focusing on the design, and the foundries doing what is called as a contract chip manufacturing. They don't do it for themselves. You will never find a chip with a TSMC labeled on it because they don't do it for themselves, they do it for somebody else. But there are still companies like Intel, companies like ST Microelectronics or Texas Instruments, which does both. That's the IDM, integrated device manufacturing. You have it listed here. Okay, and some of these, for example, Samsung also offers its fabs as a contract manufacturing. Intel so far did not offer it for a contract manufacturing, it made only its own chips. But now Intel has realized that offering it for contract manufacturing has its own advantages. So now there is this thing called Intel Foundry Services which they are trying to push. Alright, again this you might not have known completely. CE students might have been slightly more familiar with it, but in any case it's not too difficult to understand any system. You need to first come up with the architecture, then you need to draw it down to a circuit design, then you need to put it down onto a physical design in the sense of how exactly they'll be made on the chip, and then comes the fabrication, and then you do the packaging. So that's as simple as that. Again, if anybody is interested in discussing those terms in details at the end, we can. This is just to show that at any of these steps you can introduce hardware trojans. Dr. Amit here is in cyber security, so he and I were just discussing about this also. It's not as though your viruses, your computer viruses, mobile, whatever viruses are only software viruses. You can introduce these viruses or trojans in hardware also, and people won't even notice that at a particular stage, at a particular condition, your whole thing, it might be a rocket going up in the sky or it might be a warship, the whole thing can collapse just because a small trojan was introduced in the chip and was there unnoticed for years, and then at the critical moment it just fails. So this is another thing that US suspects China of doing, and that's another reason why US-China war is going on in terms of technology. Some company names, I don't know if any of these companies you've seen come to this campus for campus interview. Anybody familiar with any of these companies? Forget about coming to the campus interview. Which ones of this are you heard before? Just shout out some names. Siemens, okay. Apple, Okay, bunch of companies. So I'm glad there's some connection, right? Okay, so these ones on the top here, just purely contract chip manufacturers. These ones here does both design and manufacturing. These ones mostly do only design. These are equipment manufacturers. These are suppliers of various kinds of chemicals and so on, and the wafers, starting wafers. These here are the EDA companies that I mentioned about, and these here are the IP companies, the standard library kind of companies. And these are some of the revenue numbers. I like this chart because it splits them into, this involves only the semiconductor companies, doesn't involve the equipment makers and all, I think. It splits them into, like for example, Samsung does both design and manufacturing. Intel does both. TSMC is a pure play foundry, does only contract manufacturing. The ones which are marked as 2 here, Qualcomm, Nvidia, Broadcom, MediaTek and all, does only design. They don't do manufacturing. So this is the overall picture. So when a lot of people say that world's biggest chip maker TSMC holds more than 50% of the market share and all, that 50% market share is only for contract chip manufacturing. It's a minor point. So this is purely the contract chip manufacturing guys. TSMC, Samsung, Global Foundries, UMC, SMIC and so on and so forth. I used to work at Global Foundries. Now, why am I showing all this? Where is India in all this? Did you see India in the previous chart? Alright. We are this. Okay. In manufacturing, almost absolute zero. In design, people say, oh wow, we are a great semiconductor design powerhouse and all. The fact of the matter is, it's just as a, literally a labor supply. These people who work in India as semiconductor design folks, 99% of them probably work for an MNC, for a non-Indian company, and the revenues counted outside India, right? Salaries, your income tax, yes, in India, but the company revenue, not in India. There are a few fabulous companies, design companies which are Indian, which, you know, whose revenues can be counted in India. They add up to something like 150 or 200 or 300 crore Indian rupees compared to hundreds of billions of US dollars globally annual revenue. So we are a very, very minuscule part of that also. So that is what the government of India is trying to change. I'll come to that, but before that, just a quick chart on semiconductor wafers. The fabs don't make the wafers, silicon wafers. Many of the articles that you might see in the media and all about semiconductors will start with, oh, you know, it's sand is taken and converted into silicon wafers. The fabs don't do it. That's done elsewhere. Fabs just buy these wafers because, again, economy of scale. Somebody else does it at a much cheaper rate. So why take the headache of making these wafers? You buy them in bulk from these guys and then you process it. These are some of the equipment makers, Applied Materials, ASML and so on and so forth. That's their revenues and stuff. Smaller chips make it better. So, and this is a quiz question I was about to get at also. That's what you're trying to shrink. So this is your favorite nanometer tech node that you keep hearing, right? So this was the evolution. Somewhere in 1980s, you started getting into nanometers. What is this nanometer? Roughly, what does this nanometer indicate? I've already shown it in the picture. The length of the channel essentially, or the width, you know, the gate length of it, whatever you want to call it. That's like roughly what it is. In reality, it's slightly different from that because there's a lot of things like short channel effects and all come into picture. But overall, it is that channel length, that the one which you keep shrinking, right? We have reached 3 nanometers. Samsung and TSMC does 3 nanometers. Intel is trying to get there, and then plan is already there for 2 nanometers and so on. Now the question that I was asking, you remember that wafer sizes I showed you, 150 mm, 200 mm, 300 mm. So now if you remember that year, so from which technology node onwards do you think are made in 300 mm wafers? You remember the year? 2001. Great. So after 2001, 90 nanometer, 65 nanometer, 45 and all the way down, they are all typically made in 300 millimeter wafers because by that time 300 millimeter wafers were available and you get many more chips in one, in a single wafer. So everybody switched to 300 millimeter wafers. So if you now look at the Government of India policy for these incentives, it basically says that, well, it says any node is welcome, but it also says that it has to be a 300 millimeter wafer fab, which basically means that we would prefer 90 or below. Okay, it does not make economic sense now to go back into 200 millimeter and do some of the older ones because it's a smaller wafer. And so the companies that does this, you had, this is 180 nanometers, you had so many of them doing 180, but as it kept shrinking, the ability to do that also, the number of companies who could do it, the numbers kept shrinking. And so this is another reason why we find it very difficult now in India, because we don't have too many choices. And we have lost 30 years, 40 years. So we can't say, hey, I want to immediately start off with a 5 nanometer fab or 3 nanometer fab. This is knowledge gained over decades by these companies, and so they are not going to easily let it go. And India does not have the reputation of having tried out some of these things, right? So nobody is trying to take that risk despite offering billions, 75%, 50%, 75% in incentive. There's still a mental block for some of these companies to come to India because we are not a proven ground, and these are technologies gained over decades which nobody is going to easily part ways with or even share. And this just shows a lot of people. How many of you heard of Moore's law? Okay, master students' hands go up first. BTech? Moore's law? Okay. So it's about, the guy who basically said that every 2 years or every 1.5 years, that's debatable. Some say that he said 1.5 years, some say he said 2 years. You can, in the same area, you can pack twice the amount of transistors. That was his one law. And the second one, actually, he said that the cost also will keep reducing. So what has happened is that the scaling is still going on. You're still able to shrink these, you're still able to pack more transistors into the same area. But then the cost has not really gone down. Now it's become costly to make these smaller ones also, right? So though Dikshita said that smaller the chip, better for your performance, yes, better for performance, better for power, better for area and all of that. But money wise, it has not become that cheaper anymore, right? Okay, so almost complete with my first section. Now rest of the sections are small, but before we proceed, I just wanted to mention some quick points. I spoke predominantly about silicon fabs. Especially from the faculty side, some might be aware of compound semiconductor fabs, gallium nitride, silicon carbide. I think Kavita madam had worked on some dielectrics. She might be aware of some other materials. So just to let you know, they are all there, but doesn't come anywhere close to what silicon can do even now. And they are not going to replace silicon for the next decade or next 2 decades also. In India, yes, there is SEL in Mohali, very small fab, hardly counts. And now there is a bit of packaging that's coming. I'll talk about it when we talk about the India policy. And as I said, some design centers, design support centers of multinational companies do exist in India, but those revenues don't add to India. And a lot of people will keep saying about, oh, fabs need so much of water and so on and so forth. I don't want to go into the details of it. Anybody is interested, I can tell you the calculations and things like that, but these are all manageable for India. Skills, that's another complaint that we keep hearing. Oh, India doesn't have fabs because we don't have the skill. Well, most of these fabs in many of these places, it's not, no one else but NRIs who work. Plus, there are enough people who are knowledgeable about it in India, but just don't have an opportunity, right? So once the opportunity comes, the skill will come, and we can do training also. None of these are hindrances. And then when it comes to our, do we have the market? Do we have a demand? So those details, debatable on some aspects. Anything that is done in India should be done for globe. You should not look at only the India market and start anything, especially something which is quite costly. You should look at the globe and get this going. You will be good. Okay. Any quick questions so far? That helps me also to take a small 1-minute break. So far in the base I said, any quick questions? No? Yes? Can you maybe come front a little bit? Everybody can hear. Maybe you should, the mic is there. Thank you.
Sir, good afternoon, sir. Sir, you told about introducing malware into the hardware, sir.
Right.
We are familiar with how the malwares and viruses are with the software. Can you explain in detail about that? How malware is introduced into the hardware?
That's a pretty big topic, and neither am I an expert on that. I mean, things which we want to work in a certain way itself many times don't work. So forget about introducing a malware. I'm not to that level of expertise, but I'll show you at the end. I'll show you one slide where one small example is given. Not prepared for this talk. Just have it as a backup slide. Okay. But essentially, in a design, that particular example talks about you have to dope it with a certain amount of dopants, right? And there is all that they do is they just mark out a little box where that particular dopant has to go. You simply remove that box, nobody's going to even notice, and the dopant won't go in, and that will fail at the right time. Right?
So the hardware itself, they make some changes, so it won't be a sustainable one.
Correct.
Okay,
In the whole flow, even after the design, even after the physical design is ready, it has to go through certain changes for printability, lithography reasons, and then it goes to the mask house for making the mask. Anybody can make a twist in between the company actually submitting a design to the fab, and then it goes into the mask house. Once it's on the mask, it's stuck, right? But between that, you can mess around with it.
So how the Indian government are supporting for fabrication development within our countries? How much our Indian government are supporting?
That's what I'm coming to. Okay. Alright, but I'll have to go a little quick. It's already 11:45, so maybe in another 15-20 minutes I'll wrap up and for some last minute questions. Those who are interested can stay back and we can discuss on the slides also. So India, policies, plans, hype and reality. So history, a lot of people like to talk about, in the 80s we had semiconductor fab in Mohali, and then in the 87 it had a fire incident. Some people suspect that it was China behind that fire incident and so on. So anytime I write an article or something, some people will keep commenting on the bottom of it saying, oh, we had a fab in Mohali and it caught fire, and we had a fab in Mohali and it caught fire. Arey Baba, 30 years, 40 years after that, so what? That is gone and dusted, right? Think forward. So history is boring. I mean, except for lessons learned from it, I'm not going to talk about history. Okay. Let's talk about IPL instead, right? How many of you want to talk about IPL? Nobody? Great. Some, but not too many, not the majority. So we'll flip it around and we'll talk about PLI, not IPL. How many of you have heard about PLI? Some hands at the back. Oh man, Narendra Modi must be really sad. This is his flagship program for India, and you guys haven't, the future generations haven't even heard about it. I got to tell him. Okay, so production linked incentive is, I would say, a brainchild of Modi or his ministers or whoever his advisors are, and it has worked pretty well. What it basically tells the companies is that, hey, whatever you're producing now for a particular base year, you do more than that, and the extra that you produce, the government will give you some money for that, will give you some incentive for that. Okay. Of course, some people like Raghuram Rajan has criticized it, but we know his politics, so not going to get into that. Together with that, a few other schemes are also launched. These are basically for states to come up with electronic clusters and so on and so forth. And this was for components. We talked about those passives, capacitors and resistors and things like that. So all of these schemes exist, and this chart is actually taken from a Wire article. So those who know the politics of some of these things know where Wire stands in the spectrum of politics. So they basically wanted to tell that PLI scheme has not worked. The point is that before the PLI scheme there was no scheme, and their point was that, you guys, you promised that you will get 7 lakh jobs in this sector, you got only 28,000 jobs. It's only a beginning, right? This is going to go on. So it is, in my opinion, the PLI schemes overall is a success. Those who are interested, look it up, read both sides of it. But my point is that something is definitely better than nothing. It has worked, maybe not to the scale that the government was hoping for. It takes time, right? Government machinery is so slow, 5 years after also certain things will remain the same. So that's a different story, but at least the base has worked. But over and above this, for semiconductors, these schemes, especially the PLI scheme, the company will get the money only after it manufactures, and that also if it manufactures more than a base, what it manufactured in a base year. That doesn't work for semiconductor fabs. Semiconductor fabs has become, what is the right word? Spoiled child. Every country is offering incentive. US is offering $52 billion. Europe is offering, European Union is offering something like that. Japan is offering, China though has been offering for ages. God knows what the statistics are. So in that scenario, India also has to offer, and that also has to be upfront. Before even you make the company, before you even make the factory for manufacturing the fab, if you put in certain money, we will match that. It's called a pari passu basis. So with that, government introduced on 15th of December 76,000 crore. At that time it was $10 billion. Now it's, because the exchange rate has gone up or down or whatever. Anyway, 76,000 crore, and it wanted to incentivize silicon semiconductor fabs, display fabs, again LED displays and LCD displays. I'm not a guy on that. Compound semiconductor fabs, all other kinds of small fabs, and packaging, and of course the design also. So not going into the details of it. This is like the finer details, and the first time in December or 2021 there were certain criteria, there were some deadlines. Government realized it's not working. I mean, people like me, for example, it basically, they said if you're doing a 65 nanometer fab, will give 30%, 45 will give 40%, 28 and below will give 50%. Day one I told, bad idea, just make it equal for all. I tweeted with the ministers and all tagged. 8-10 months later, government had appointed some advisory committee members and all, half of whom have no connection to semiconductors. The other half, or no, other 2 or 3 people who have some connection to semiconductor industry is outside India. They're not even Indian citizens. 8-10 months later, government said, sorry, mistake, we make it equal for all nodes. So this is how government works, but they changed it to 50% for all nodes, changed the deadlines and so on. It's going on. Now, the hype versus the reality. She said, took some various names, UP, Noida, this, that. Nowhere, nothing has come up. That's the reality. 3 years or 2 years after the policy, what has been approved? Silicon fabs, none. Display fabs, none. Compound semiconductor fabs and packaging. Out of packaging, Micron. If you heard the recent news, $2.7 billion or something packaging unit. That's a pretty big cost for a packaging unit. Never mind. Micron is not an Indian company. Again, the revenue will be counted outside India. Never mind. Something is better than nothing. And the design also some 5 out of 26. And when there's a whole body that was formed, India Semiconductor Mission, that's supposed to be the nodal agency to review these applications and decide and so on and so forth. When this body was formed in December 2021, January 2022, they said we want a CEO who is 25 years experience in semiconductor industry, out of which 10 years should be at least outside India. Anyway, if a guy is 25 years experienced in semiconductor industry, half of his time or probably whole time will be outside India. There's hardly anything in India. But in any case, we want such a CEO, we want such a CTO. Guess who is the CEO right now? 1.5 years after formation of that body. The CEO right now is a on deputation part-time CEO from Ministry of Electronics, IAS. Okay, nothing to do with semiconductors, nothing to do with engineering. This is the situation of India government. 2 years, applications are sitting there. 3 applications were there for Silicon CMOS, Vedanta, Foxconn, ISMC, IGSS. Vedanta, Foxconn, from day one, people like me started writing, neither of them have experience in semiconductor fabs. They need to get technology, they need to license technology. 8 months, 9 months down the line, I know, ministry started discussing whatever they submitted, is it valid? They submitted a proposal or technology from a research lab and all. I had to write articles saying that doesn't count. In your boss, read your policy. Your policy, it says that production grade technology license is needed. This doesn't count as production grade license. 8 months, 9 months after that, they told Vedanta and Foxconn that this doesn't count. Go hunt for another technology partner. 15, 16 months lost, all the 3 proposals rejected. Do you really need 15, 16 months to know that? Somebody who was experienced enough sitting there would have known in 2 or 3 months. If it is reject, come back, right? So much time lost. There is hardly any, expertise there. They're just dragging it. But still, I repeat, something is better than nothing. One day, hopefully, these all will materialize. Okay, forget about the government. The master student person, does it satisfy? We can discuss after the talk also. I'm neither pro-government nor anti-government. I go with, I'm a practical guy. I want it to happen. That's all. Okay. Feeder industries and software, again, rather fast. Just to show that even building the fab, you need so many engineers, right? The floor planning, so you need specialized architects and so on. Inside the fab, how the various equipments are arranged. And there's a little term here, if you know AMHS, it's called Automated Material Handling System. How these things go, they're all automated, robotics. So robotics has an opportunity. I was talking to the department head, he's in power systems. So I was telling him, power systems an opportunity because the fabs need uninterrupted and non-fluctuating power. So, you know how our grids are. So you need a backup power system, and you need to also ensure that when one fails, the other kicks in without even the system knowing that the other has kicked in. So these are all opportunities that exist. PhD student must be happy with this slide. There's an equation which I don't understand head and tail about, but that's needed. This is just to, before processing the wafer, you need to spin it and coat it with resist, or you need to put a photoresist on it. Just to ensure that the photoresist thickness is uniform across a 300mm wafer, you have to apply all this physics, right? And then the final equipment. The point is that each and every piece of it needs physics, needs chemistry, needs whatnot. And this is an equipment just to cut it. Just look at it, right? It's not your take a knife and cut it. You have one 300mm wafer and you have 150 or 200 dies in it. They're not cut, there's not somebody sitting there and doing it, right? You have an automated machine for that also. So everything is automated. Everywhere there is an opportunity. Again, different pieces of the puzzle, not going into the details of it. When I talk about the opportunities for universities specifically, I'll cover a little bit on some of those. Used from Times of India, or we used to call it a different name in our bachelor's time. Pramod might remember. Never mind. Chip making needs a lot of software talent today. Software, okay. He also, in the interest of time, I cannot go into the details. Neither am I a software guy. My wife still works for Global Foundries, but she doesn't know head and tail of semiconductors. She works on the software side of fab automation. So sitting in India, the fab is in US, fab is in Germany, fab is in Singapore, but the Indian team, Global Foundries has an office in Bangalore. There are people sitting here and controlling or operating this fab or watching, monitoring, reporting issues. Imagine in US or Singapore or Germany, when they sleep, the India team will be awake, right? So these kind of things and anything, as I said, design needs software. The EDA tools, it's nothing but software. Making the photo mask needs software. Operating these equipments needs software. Moving the materials across these equipments needs software. Analyzing the yield needs software. Selling it and counting your accounts and things like that needs software. So software runs across board. Okay, final section. Hopefully 5 minutes, and then we'll talk about we'll take questions. This is again not too sure how much relevant here, but the universities there is within the wafer, within a die itself, you can have shared space. Real estate is costly in real life also, in the semiconductor world also. So a university might not be able to pay for the entire die area. You can share it. You can share it with other universities. There are, like in real estate, there are brokers. Here also there are brokers. I don't want to call it brokers. It's a very reputed, Moses for example. They will coordinate different universities' designs as long as they are on the same technology node and so on and so forth. And it's based on something called a PDK, physical design kit. So they will put it together for you. Okay. So there are enough ecosystem, not in India, elsewhere that exist. These are things which Indians could have done. These are things which we can do still, right? But you know that whole mentality has not been there for 30-40 years. Yeah, Ministry of it's a ministry page, and you can already see, right? There are so many something written there, and you need to spend one whole day to figure out what is what. But in any case, SMDP1, SMDP2, SMDP-C2ST, understood? That's how ministries work. But nevertheless, it basically is a program called Chip to Startup. Doctor wanted to talk to me about a little bit about startups also. Government has some programs. Unfortunately, you know, many of these things, I got a WhatsApp forward, I'll tell you the gist of it. You need to submit an application for a particular design, for a particular product. This one particular company or startup submitted it. Submitted in March of 2022. Waited. In between, a Chinese guys came and offered them money. The product is out. I mean, they ordered it to the Chinese guys, they sold it to the Chinese, product is out. The file for the India government incentive or whatever is still sitting in MIT, in the ministry. This is the situation. Final word on the research. Maybe I have one or two more slides, but just a word on the research. A lot of you know, PhD work or master's work, you can do a lot of papers and so on and so forth even in this world. But keep in mind, an academic research is way different from an industrial research. Do not expect that in a university, sitting in a university or a group of universities can come up with the entire process technologies. Or let's solve universities, let's solve IITs. The IITs in India are demanding that. Give us a lab and we will come up with the latest technology node. Not going to happen. Okay. The real technology node is developed by industries over decades of experience. You can do bits and pieces of it in the academic world. The scale is different, the thrust is different, everything is different in academia versus industry. But academia, if you can collaborate with industry, you will know exactly what are the industrial needs, what is the piece of the puzzle that you can sit and do in a university and solve. For example, I told you the power system, the uninterrupted and non-fluctuating power, it's probably easier to do that in the US or Europe. Can a university take up a study of how is it in India? What is it needed in India to achieve that, right? What are the suggested, your primary source of power, your secondary source of power, and if needed, a tertiary source of power? How will these things talk to each other? These studies can be done at a university level, right? And many more examples. And a bunch of other things. Again, I think this is my last slide. If anybody wants to know how exactly some of these terms relate to the semiconductor industry, we can talk. But the point is that a lot of these are connected to the semiconductor industry. I'll just take one area out of it, which is the AI/ML area. I'll take just one journal or one online portal called Semi-Engineering. It's a portal dedicated to semiconductor engineering, to fabrication and design and so on. But that's just one portal in 2023, which is not even complete. Just look at the number of articles it has published, which has either an AI or an ML mentioned in it, right? So just gives you an idea of even this one, the kind of scope that it has in the world of semiconductors. Okay, so you can say, maybe I'll end with this small, let me see if I have that time. Yeah, it's already 12:03. I'll finish it at 12:05. My contacts are there. So in the introduction, we were told that I do have an interest in Sanskrit and Indic studies also. So I do conduct, I haven't learned Sanskrit formally. I just learned it from Samskrita Bharati, just a spoken Sanskrit. So we do conduct some spoken Sanskrit workshops also sometimes. So there is this little example, I'll do a little demo here. So, Kupi, Duravani, Kupi atra asti, Duravani atra asti, tatra asti, tatra asti, tatra asti, sarvatra asti. Understood? Ha. So we also say that devaha sarvatra asti. So devaya namaha. Duravani sarvatra asti. Duravanyai namaha. So likewise, semiconductor sarvatra asti, and in semiconductor or in semiconductor industry sarvam asti. Every other industry has a role to play in the semiconductor industry also. It works both ways. It's almost like a feedback loop, right? You make a chip which is very specific or which can do things on the artificial intelligence or machine learning front, and in the semiconductor industry the same chip will come back because the artificial intelligence or the machine learning has a use in the semiconductor industry also. So that's how it works. Let me stop formally. We'll take questions. Thank you. I see some paper being distributed. Questions, anyone? Please. You had a mic? Yeah. The front bencher is asking a question. I had an advisor in a US university, just a small joke. One of my advisors when I was doing my masters, you know, any presentation any student does, he'll be sitting in the front and he'll appear like he's dozing off. But then, you know, somewhere in this presentation, he'll just lift up his head and ask a question which is damn on the point of where you're talking about. Never figured out how he does that. But any case.
Sir, good afternoon, sir. Sir, actually you said that that semiconductor was invented in 1970s, right?
IC was first made in 19. Semiconductors goes back to...
during the 1901 or 1902, I don't know
Correct.
exactly. But a scientist, that invention, he patented as cat whiskers, usually semiconductor, right?
So, BOSC, right? We Malayalis will end up pronouncing it as Bose or Boss or whatever, BOSC. Which Bose, I don't remember now, JC Bose, I think. So, he had a patent on, you may sit down. If that's the end of your question, you can sit down. You had another question. Please go ahead.
Sir, whether that by using semiconductor and kinetic energy, we can produce the electricity. For example, in the road, if we apply that semiconductor chip, right, the vehicles run based on kinetic energy, so we can produce electricity.
Okay. Any other question related to that? Okay. So there are two parts to it. The first part I'll just quickly finish. Yes, there is the first patent in semiconductor belongs to an Indian. Give it a clap. At least we have something. You know, unfortunately, we never converted it into an industrial, experience. And you can email me or tweet, tag me on a Twitter. I can give you the enough references on that. The second part of the question is basically, look, it's not as though you can just put a semiconductor material on the road and it will convert and automatically give an energy. There has to be a system in place. Okay. For example, there are something called a gas sensor or a pressure sensor. Inside it is all semiconductors. Or there is an entire area called MEMS. MEMS is micro electromechanical devices. So small cantilevers, systems which used to be done on actual big things, now can be made on small semiconductor, pressure sensor. So a stress applied on a particular semiconductor material converts into a certain amount of pressure. It can convert into a certain amount of electricity. You measure that electricity, you know what the pressure is. But these things need a system. You need to convert that idea, you need to convert that property of that material into a system which can be put on the road or wherever you want to put it, and then only it will work, right? So that is the gap, or that is the area that you need to travel in between just an idea, just a theory. This is the difference between an academic paper and an industrial R&D. Hope I answered it to some extent. The specific case of converting the energy into a, yes, there are various things which can, photovoltaic cells, what does it do? Convert the light into electricity. What is the principle behind it? What did Einstein get Nobel Prize for? So Einstein is a funny story, right? This guy had invented theory of relativity, general theory of relativity, special theory of relativity. Nobody understood a damn thing. And then they said, next time he invents whatever it is, we'll give him a Nobel Prize. So 1905, Einstein said the photoelectric effect, damn, give it the Nobel Prize, done. That's how the story goes, photoelectric effect, right? So the point is now, in 1905, when did solar cells become popular and come into real life? Just recently. What took it so long? The efficiency was so bad. The efficiency, you know what is the efficiency of a most recent solar cell? How much of solar energy it actually captures and how much of electrical energy it gives out? Any guesses? 18%. 13%. If I stay more, it might go even down. So let me stop there. Yeah, somewhere in that range, right? After 20, 30, 40, 50, God knows how years of research, you still can't get more than 20% efficiency out of a solar cell, right? So that's the difference between an idea and a product. But fight for it. If you guys don't fight, the government will keep sleeping for years. But if you fight, you know, give them 10 punches, one might have an effect. Okay, any other question?
Good morning, sir. If it's difficult to start a company,
It's become good afternoon already. You didn't realize.
sorry, yeah,
It's okay.
yeah. So, if it's difficult to begin a company here and with the policies, can't the NRIs start it there and maybe we can ship our talent
Ship
there,
the NRIs?
whatever, whatever it takes. Yes.
Sure. We will need to ship in some NRIs. That's a different story. But yeah, there are various opportunities. I think I was mentioning to him in the morning. I keep getting emails. I have 100 crore to invest. I have a 500 crore to invest. Sir, please advise. I'm not a sir, but still, sir, please advise what is the best place to put it in. One of them, he is currently in a garment industry outside India, somewhere in South America or something. He wants to invest his money into electronics. I said, okay, fine, but you know, caution. So after half of them, after talking to me, he says, oh, this isn't as easy as I think. So the point is that there are opportunities, but it's not a child's play also. You will need proper guidance. You will need to analyze it, to the detail level. But then you need both. You need that risk-taking mentality also. You need enough guidance also. So the generic answer is yes. You can have. There's a person who contacted me. You know these equipment makers. I told you some of these equipment cost $100 millions and $200 millions in dollars. You know, there are people who supply parts to it or make miniatures of it, and there are even PhDs. Since he is a PhD, I know personally never met. Most of these are over emails and all. There are people who, after completing their PhDs, got into it, started making small equipments, growing slowly. Sometimes they get some funding, venture capitalist or whatnot, right? They had a tough time during Corona, but they still, they're still hanging in there. It's happening, but the scale is not yet reached. Look, we are 30, 40, 50 years behind. As simple as that. We slept. India slept on this entire opportunity for 30, 40, 50 years. Now we are waking up, or sometimes pretend to be waking up. It will take time. That's why I keep going and giving these talks, right? At least the next generation, take it up as a passion, push, keep it going. Small, medium, big, doesn't matter. We need everything. Okay, specifics, I'm most welcome to talk to you separately. You can email me, we can discuss. Any further questions? Okay, anything from any faculty side? No? Okay.
If any particular material is chosen, what are the properties we have to take a look at?
Yeah. Thank you. As I said, didn't intend to cover it in deep, but I'll answer it to you quickly. First of all, silicon is a base. Silicon is the starting material. But when it gets to advanced technology nodes, 2 nanometers, 3 nanometers, and so on and so forth, There are even within that chip, there are certain other materials, for example, silicon germanium. So if you know, there's a property, I mean, there is this mobility factor. So increase the mobility, to increase the speed. This some of the details of how the advancement has happened in 3 nanometers, 2 nanometers. It's amazing stories. What you can literally see happening at a macro scale in terms of your building architectures. For example, 20-30 years before, there was, I don't know if this can be called a false ceiling, but 20-30 years before, there was nothing called a false ceiling. Now every apartment flat will come with a false ceiling, or the kind of construction differences and so on. Almost all of that or even more complex things has happened in this nanometer scale. You literally, from a silicon channel, channel is the most important part, right? That's where it happens. So to go into the physics of it, the NMOS and the PMOS. For the NMOS, the silicon mobility is good enough, but for the PMOS, it isn't. So you literally scratch out that little part of the channel silicon and replace it with silicon germanium or sometimes carbon and things like that. So to that level, a lot of material is already going into the existing silicon chips. Another example is the dielectric. The MOSFET metal oxide semiconductor. It is no more oxide. When you have the, your volume is shrinking, you need a thinner dielectric, and that cannot withstand higher voltages and so on. So you already gone into things like hafnium oxide. It's no more silicon dioxide, I meant, right? So much innovation has happened at that level. The second part of it is, what about the starting material itself being different other than silicon? So there's gallium nitride, silicon carbide, gallium arsenide, so many of them. Each one of them has their advantage versus disadvantage. Some of them offer better mobility, some of them offer better power capacity and so on and so forth. But none of them have reached the scale of silicon due to, in my opinion, predominantly one reason. The methodology to grow a single crystal silicon, at least to the size of a 300 millimeter wafer, is now perfected. That has not happened in any of the other materials, gallium arsenide or gallium nitride, or none of them. They're still at 200, 300 and all, and 200, 150 and all, and still with a lot of defect. And a single defect can kill your chip. So that's one fundamental reason. There are other reasons also why none of them are picked up. But they all have their applications, like electronic vehicles, for example, or power chips. You will never see, almost take it from me, for the next 20-30 years, you will never see a processor chip made out of anything other than silicon. But you will see a power transistor or let's say EV battery handling system chip made out of silicon carbide or gallium nitride. They are small chips, few transistors. VLSI, millions of transistors, billions of transistors, processors, silicon, at least another 20-30 years, even beyond. Okay, I think that will mark as the final official question. I can hang around for a few more minutes if there is any unofficial question, but yes, please, you may do the honors.
Winding up with the questions, I would like to thank Sir for this informative session. I believe our students will have a lot to take away. Your depth of knowledge and engaging delivery truly enlightened our audience and provided valuable insights into semiconductors. Before we conclude, I would like to extend our heartfelt gratitude to each and every one of you for gracing this event with your presence. Your enthusiasm, engagement, and support have been instrumental in making this gathering a resounding success. We are immensely thankful to our esteemed chairperson, Dr. Balamurugan sir, along with the faculty coordinators, Dr. Amit Agarwal sir, Dr. Ilango Karupasamy sir, and Dr. Kavita ma'am, and dedicated team whose relentless efforts have brought this event to life. Let's carry the inspiration and insights gained here today forward as we continue to shape the future together. Thank you.
Thank you everyone, and be in touch, those who are interested. This is the slide for the master student who asked about the hardware project. So this is, I remember those little child magazines where two pictures will be given and say, figure out the difference, right? How many differences can you find between picture number 1 and picture number 2? So the physical design this and physical design this, find out the difference. That's the cause. Okay.